Okay. So, ladies and gentlemen, welcome back to class. We're going to have two major topics explored today as time allows. The first topic will deal with a cluster of issues having to do with performance. And specifically, we'll be looking at performance concerns, the use of important tool, profilers to assess performance. And then we'll be looking some at using those profilers, getting a sense of the performance cost of functional abstraction. Okay? But also, at the same time, giving a sense of the performance advantages of functional abstraction, which may not be obvious at first glance, but which are powerful when considered collectively, and I would argue well outweigh the cost. We'll then be talking a little bit about optimization of code, both as conducted in an automated way by a compiler and as performed in a manual way by yourself, particularly focusing on performance bottlenecks identified often through profiling. Okay, so that's topic one, and there's a decent chance that that may last out the full time we have together this morning. However, as time allows, we'll be going in and starting to systematically explore the use of higher order functions within a set of very commonly used primitives for manipulating them in a functional context. And that will have to do with the use of a mechanism called map, which systematically takes an element of a collection and transforms it to a new element of an entirely new collection of the same size. Filter, which would filter out elements of collection, specifically obtaining those that match a certain predicate and creating a new collection of those. And finally, reduce, which will take a set of elements in a collection and process them to yield one single result. Not a collection, but one single result for that entire collection. So I might add them together, might multiply them by each other, etc. So those will be following us for potentially some of this lecture, but certainly the next lecture or two. And it turns out they're really important. And understanding much of today's parallel hardware and the way in which it's used in very practical ways has to do with use of those primitives. If you've ever heard of map-reduce algorithms, for example, which are quite central to high-performance computing as conducted by the Googles, the Facebooks, the Twitters of the world, etc., they centrally involve these primitives. And so much of parallel programming today is shaped to allow us to scalably achieve parallelism by manipulating those sort of primitives in many cases in a functional context. Okay, so we're going to be seeing quite a bit of code today and some slides. And pursuant to that, I'd like someone at the back to get the front lights here so we can. We have a standing order in on that projector, and experience suggests today that it's not yet delivered. I'll see if I can check on that again. Okay. So, ladies and gentlemen, I had asked you to undertake an assignment here. This is this home exercise, where I asked you to examine, using a profiler, performance for several different versions of this code. And within each of those, I asked you to further So to examine each of these, and then I further asked you to examine it across different levels of optimization. So here we were looking at the performance of the sort of original code, which was devoid of significant functional abstraction. It had one function to rule them all. What function was that? Main. A refactored version, which had lots of functions named with intention revealing names, designed to make it easier to understand that program, yes. Make it easier to test, yes. Make it easier to divide up the work. Make it easier to evolve. But also, as we'll see today, to make it easier to optimize and to make it easier to assess where the performance is where the performance costs are. So this is one that had lots. Number 2 had lots of functional abstraction, and number 3 here is similar to 2, but it also has this this ability to sort of choose different rules for updating a cell. In this case, based on command line inputs. Okay, so those are the 3 that we were comparing, whose performance we were comparing, but we were doing so in a kind of matrix way conceptually, where we were comparing these against each other, but we were further comparing them in the context of different levels of optimization here. Okay. Now, the goal for this, so this exercise took place using a particular set of tools. The GNU C compiler, GCC, and the GNU profiler, gprof. Those tools are not particularly privileged, although they are very widespread. They're widely used, and even if you don't use C yourself, they're often used in the background to compile things for your for your computer, etc. So if you're using Ubuntu and you do an apt-get of some program to download, or you install a new kernel or what have you, GCC may be used in the background to compile things. gprof is a very old profiling system, but it's indicative of the type of information you get out of today's profiling systems, whether for Java, for Python, for Ruby, or for C. Okay, so don't get caught up in the particulars, but try to draw some broad lessons. Okay, so I asked you to experiment with this, and I'd like to ask you what sort of findings did you get out of it? I'll show you mine in just a moment, but what sort of findings did you come away with from that? So, performance costs associated with these different versions of the code?
Functions really are bad if you don't optimize at all.
Ah, okay. So here's the ugly component, the ugly one, right? Do I have to show that to you to remind you? Or is it the face that you never can forget? Okay, let's go take a look. Come on. Come on, it's like the Medusa of code. Okay, so there we are. And this code I'm going to come back to, okay, a couple times, because we're going to see that there are some elements in this that were put in deliberately to try to speed the performance of it, okay? And we're going to see how with functional abstraction, we can get basically all the functional abstraction we have and still get all these performance benefits, okay? That'll be later in the lecture, but we'll see that. And so take a look at this code. So there's lots of problems with this code, but it has some virtues to recommend it, and when it comes to performance. And one of those virtues has to do with the fact that there's something different about this code that's very different about the innermost structure of it. What is it?
Everything is simple math.
Everything is simple math. And basically, rather in place of the code here, whose innermost components involve looping. For example, this count of surrounding live cells involves 2 nested loops, for example. Here, we actually have code that's more or less unrolled. Those loops are unrolled. They're sort of written out. They're dealing with these various corner cases, these various sort of conditions on the edge, but they're played out. We're not looping over it in a very general way and over this sort of 9x9 area. We're actually playing, or excuse me, a 3x3 area with the 8 different possibilities if you exclude the center. Instead, we're kind of writing these things out directly. Okay, and so this code was written to be lean and mean. And indeed, in my youth, I saw code like this written out for similar programs. I remember seeing that and remarking that it was really optimized for speed. And one of the things we'll see here is that if we consider the non-optimized code, the unoptimized code, this carries with it for 50,000 iterations of the loop, 8.4 or so seconds. Turns out this isn't on, I did it on a different machine previously, so I'm not showing it on this particular machine, but 8.4 seconds. Here we have, with functional abstraction, 52.3 seconds. Wow. Wow. This is, over 6 times the amount of time taken here. So those functions are costing us something there. Here with cell rule abstraction, it's slightly larger. Here we're calling through pointers to functions, but that's a quite small difference compared to anything we see here. Right? This difference is big. This difference going from calling directly to function A versus calling it through a pointer to a function, very small difference. Okay. Observation 1. First glance, naive glance, functional abstraction costs us big time. Okay. Let's look a little bit more closely at the situation, and much of the lecture will be designed to do that more broadly. Okay, as we go to optimization, how does the performance cost of the code in general, abstract away for a moment whether we're dealing with the functional one or the one with lots of functions or the one which has one big function to rule them all, how does the cost go down as we add optimization in? As we start optimizing, as we're looking for opportunities to speed the code up?
Pretty drastically for all of them.
Pretty drastically for all of them, yeah. So 8 to 3, it reduces it by over a factor of 2, right? 52 to 11, right? We're reducing it here by nearly a factor of 5 times. And 52 to 11 again. Okay, so those are pretty big differences. Basically, you could get almost the performance, not quite, but start getting close to the performance of the code with no function, with only one function. Code that's hard to read, hard to reason about, hard to debug, hard to test, hard to divide up the work, etc. You could get to the ballpark, certainly within a binary order of magnitude of that, just by turning on optimization. Okay, without having to go restructure the whole program to try in an attempt to secure performance, we could turn on optimization and get pretty good performance out. Okay, compared to this. So with optimization on, we are in the ballpark of this. Not quite there yet, but in the ballpark. Now with level 3 optimization, so a whole nother level, and we'll talk about what some of those look like, we're getting something which is almost twice as fast as the sort of naive version without these divided functions, without optimization. So in short, with a serious attempt at optimizing, but purely on an automatic basis, flipping a switch, we're getting performance out of our system here that rivals or exceeds that of this system here without optimization. Okay, so you may think, okay, I'm making this lean and mean. It's close to the machine. It's going to really have great performance because I cut away all these functions. Not so fast. You can get that sort of performance with optimization turned on from code that's really well structured, divided up into understandable pieces. Okay. Now, someone could say, rightly so, well, yeah, that's true, but with optimizations on, I can get even better performance out with this one. And fair enough, this can get down to 2.7 seconds here versus 4.1 here, right? That's a fair difference there between those. And we'll come back to how you can best this while still keeping your function, still keeping the structure of the code with a little bit of attention, getting hints by the profiler that you would never get with this code base. Okay. Okay. So big picture. First blush, functions hurt us performance-wise. Second big picture, with optimization, we can eke out almost all the basic advantages of operating without functional abstraction from code that's really well structured. This doesn't mean forsaking forever performance, having these functions. We can get that level of performance, that zone of performance with well-structured code, with attention to optimization, without even lifting more than a finger in terms of turning on optimization options. Some big picture understanding there, but we're going to probe this a little bit more. Okay, we're going to be going into more detail about why, in the big picture, it's likely you'll get much more performance out of code bases more like this one, the second and third one, than out of the first one, once you look beyond a very narrow myopic view. Yeah?
So is there any reason you don't want the optimization flank on other than maybe slightly shorter build time?
This is a good question. So this is a great question, Warren, and I welcome it. So I'm going to ask anyone, before I give several reasons for sometimes not operating with optimization, I'd like to ask people here. Yeah.
Some optimization flags change the behavior of the registries so that you can't debug, you can't do a data dump and debug it.
Exactly. So optimization does impact, does interact with the debugger. And if you turn on optimizations, there's certain structures in the code that you might see when in the code base, and when you're debugging, you expect to see them, but they've been elided out. They've been removed from the code, or they're no longer captured in the optimized code because it's done it in a more clever way. Function inline, as we'll see, is a big one. We actually take something that apparently is a function call, but the compiler is smart enough to inline it, meaning it's given in the source code as a separate function, but it actually takes the body of it and substitutes it in where it's called. There's limits to that. When you're calling through pointers to functions, there's real challenges with doing that. But it can be a very effective technique for for avoiding overhead associated with small, frequently called functions. Another case, it may turn a loop into a set of straight line statements. So these are transformations where you might expect, to be able to enter when the call takes place. You can enter that function, and suddenly that function call is not taking place. So that's one of the reasons. How about another reason? Yes.
It'll optimize for space instead of time.
Yeah. So, good. So, it turns out that there's different options in GCC, and many of them are aimed at speed. Some of them are aimed at space, and sometimes what you get out of the optimization is not the balance of space and speed you're thinking about. When would you be concerned with space? Yes.
Small portable machines. Like
Yes,
machines, yeah.
exactly. Small portable machines, embedded hardware. You're compiling a larger code base for a tablet. That's a big thing. What's another time you might care about space? Well, if you're dealing with lots and lots of data, and perhaps if you're applying things in parallel to it, you're on a machine which has lots of cores on it, perhaps, and you've really got to make use of the limited memory on that machine. So much of what we do in data science these days, so much of what Facebook and Google do to earn their bread and butter operating with large-scale data, it's very space sensitive, because when space gets used, too much space gets used by our programs, what happens to the speed? Yeah, speed goes way down. Why way down?
Because it might be crashing or something.
Yeah, so there's this, maybe folks remember from 2.14, from 2.15, from 3.32, I think you would have seen it. All these courses, if you took them, and I know many of you have taken them, many have taken at least subsets of them, you would have heard probably about memory hierarchies. You have, in general, faster storage and slower storage, but there's more of the slower storage and less of the faster storage. And much of being intelligent about computation beneath the covers is about trying to get as much of the important code to run in the small, fast memory compared to the slow, large memory. And if you're using too much space, you inevitably get pushed down to those lower levels of where it's slower but larger. So we have virtual memory that's paged to disk, right? So it gets put onto disk because it can't fit in the memory of the computer. So, my machine, there was 16 gigs, right? That doesn't mean I'm limited to 16 gigs of programs and data. What it just means is if I go over that, it'll start swapping it to disk. It'll start putting it out to disk. Stuff that needs to reside in memory later, but isn't needed at the moment gets put down to disk, and stuff that's needed right now gets brought back in. And the disk thrashes sometimes. But it's not just disk. Disk is, I don't know what the statistics are these days. Like reading something that has to be paged in compared to reading something in memory. It may be a difference of 1 million or something right now in performance. But that's not the only hierarchy. There's several levels of caching associated with processors these days. You have a level 3, a level 2 cache, and you have main memory. And if you're using space inefficiently, you're going to be going to main memory when you could have gone to level 3 cache, to level 3 when you could have gone to level 2. And so there's these different issues. So sometimes space, using more space means using more time, just in ways that aren't immediately obvious if you run it in a standard profiler, but once you're dealing with a memory-constrained environment, it's clear. So optimizations interact with that. Optimizations may also interact with profiling in odd ways and with other tools. But finally, And in languages like C, languages like C, some optimizations are, can you fill in the last blank of that sentence? Begins with a U, ends with an E.
Unique.
Good call. I won't dispute that. Some optimizations are unique to C. Yeah, I mean, there are some that are sort of distinctive. But I was thinking about something that was an evident. Unsafe, ladies and gentlemen, unsafe. It can't figure out what the heck we're trying to do. It doesn't know that this thing that looks like a pointer to a double secretly points to a structure. And so it twiddles something and says, oh, I don't have to look that up. Or maybe it's pointing to something that's volatile memory, and it's this low-level code, and that thing actually changes. And so it says, oh, I read that before. I know what the value is. It doesn't know it changes out from under it. It doesn't know that two pointers point to the same thing. So when you read from one many, many times, it says, I don't need to read from that each time. I'll just create a variable, get it once, and then use that on an ongoing basis. But meanwhile, another pointer is writing to that same location. And when you get a variable from it up front, that variable stays the same, but meanwhile, the thing that you should have been reading is changing because this other pointer is writing to it. C has lots of weirdness. Okay? And C has the ability to be loosey-goosey about things that matter to a compiler. So when you turn on -03, sometimes it doesn't work. And let me show you something, if I may. Nope, it's in here. Okay. Which one? Okay, let's go take a look at this one. Okay. You can see what I was doing last night. Man GCC. This is one of the larger man pages in Linux. Unix. Take a look at this. Yeah, this goes on for a long time.
We're only at F.
So we won't be covering its entirety during today's class. Yeah, we're up to 4,000 lines, right? These are all the warnings. Okay, these are optimization. Okay, hey, there we are. Okay, so this is exactly the one I wanted. Not bad, if I may say so. Fast. Disregards, so this is this plus plus. Or minus minus. It depends how lucky you're feeling today. Okay? Disregards all strict standards compliance. OFAST enables all -3 optimization. Also enables optimizations that are not valid for standards for all standards compliant programs. So it turns on these particular ones, right? You notice, by the way, optimized debugging experience. Optimized for size, reduce compilation time, optimized yet more. Now, here, you can actually get a sense of the particulars, right? Inlining functions. It performs some intelligent restructuring of loops here. It can further do, I think this is cloning maybe code that's calling up the same thing. It creates separate copies of it. Perhaps I'd have to check. But it does some very significant optimizations here. O2 does fewer. And a lot of these are sort of bread and butter, powerful optimizations. And they include some ones that have significant cost for compilation time, for example. Inlining small functions here. There's some floating point ones here as well, and partial inlining, cross jumping, etc. Lots of stuff here that it's really sweating the details of performance. So these sort of optimizations are mostly safe with C programs if you're careful in your C programs, but occasionally you'll run afoul, like -03, your program will break. It exhibits errors when you run it with -03 that it doesn't exhibit if you run it with -02 or no optimization at all. And the ability to turn the optimization on and off then is very important. Because if you're getting this crash from -03, you might want to see, does that occur without the optimizations on, and try to figure it out. Okay. Okay. So a lot of details here, but fundamentally, you can turn on and off certain types of optimizations. Delete null pointer checks, assertions. It might hurt your ability to assert things. Assert this pointer is not, is not null, or checking it prophylactically during the code. It may delete it out from under you. So here, you have the option of turning these things on and off using these -f commands. Okay. Okay. So optimizations are important. They matter. Let's talk about them a little more here. So first of all, if you're interested in what optimizations are doing behind the scenes, you can use GCC -s. Okay, and this will actually produce an assembly language version of your code that you could see, for example, oh yes, things have been inlined, or things have not been inlined, or what have you. GCC -s, okay? Just like GCC -e will do the pre-processing step and output C code that's the pre-processed version of the program. So you see all the all the pound includes, performed and inserted into the code, and you'll see all the pound defines replaced with the actual, or the things that use those, refer to them, replaced with the pound defined definitions, etc. These are very useful flags on GCC. But let's talk about profiling. So in this code here, I asked you to perform profiling, and it's the -PG option. Okay, and I asked you to then run gprof. What did you see out of gprof? What came out of it? Okay, good. Times came out of it. Here we go. Okay, so here's an example of code that was taken out, and you'll notice first that was okay. Excuse me. That's one I didn't want to look at. This is the one I wanted to look at. Okay, ladies and gentlemen. Here I ran this profiler on the code with the functions in it, and you'll notice it put out a profile of that code, and this profile consists of two major areas. This top one, which is very focused on sort of where most time is being spent in terms of methods, and then this lower one, which is more focused on those methods and how much time is being spent in them versus their children and how they are being reached. Okay? So you'll notice here's some statistics. Okay, we have, what is that? Is it 100 million? 100 million calls to count surrounding live cells, for example. 100 times 100 times 100, etc. Count surrounding live cells. And what we see is that of the time required for this program, 50% of it, this is the most important statistic to look at, 50% of it is being spent associated with that code. And that includes what it's calling. Okay? And here, the next one down is legal coordinate. It's about 19%. Index for row call, 17%. And update cell, update cell about 9.23. So sort of applying the Pareto principle, 80, in this case more than 80, right, percent of the time is being spent in just the first couple of these functions. Do you see that? Right? We had this 50% to the 19%. Already we're right up around 70%, and it's like 87% of the code of the time is being spent in these first couple. Okay? And you'll notice that, to say, okay, there's 6.18 seconds associated with count surrounding live cells, another 2 seconds associated with is legal coordinate, and this cumulative is sort of totaling up all of these ones above it, and this one here. So 6.18 plus 2.33 is this 8.51 there, right? And this 10.60 is just that plus this 2.08, right? Okay, so we see a very large fraction of the time. As we run this code, it's not that the time is just diffusely spread around the program, that it's just sucking it up, all around the program. It's certain particular areas of the program that are the hot spots. You got that? Certain particular components. Now this is important for what reason? How does that help us? We know what the hotspots are.
If you want it faster, make that part faster.
We want to make that part faster, ladies and gentlemen. We could focus in. Let me counterpose a question. What would this profile report look like if I did the same type of profiling with gprof and so on the original code base, the ugly code base?
It's one line.
One line.
No, it's 3. Technically, it's 1 for the main and 1 for the X-thing frame thing.
Okay, yeah, that's right. So basically you see, okay, main takes a lot of time. Not very informative, ladies and gentlemen. You're kind of flying blind there. Well, where in main? What part of main? Where do I need to focus my efforts to make it faster? It's not obvious to you. Main. Here, it gets pretty obvious what's hurting us. And because it's obvious, because it's identified those areas of code, we have the requisite extra information to go change it to make a difference. And we don't have to simply supplicate ourselves and say, well, okay, let's rip functional abstraction out of the entire program. Let's eliminate, exterminate all function boundaries to achieve performance. That is not a fruitful thought. In fact, it's a very dangerous thought. It's the fact that we have function boundaries that allows us to recognize where the real cost is and allow us to focus on those areas. And what we can do is focus on those areas and figure out how we're going to optimize them. And if that means sometimes saying, okay, look, this is a separate function, but we'll restructure it so it's not, and we'll reduce the cost of, by 50% by just changing that one thing. That's a very minor sacrifice. Very localized change. Very conscious sacrifice of functional abstraction for that 1 or 2 functions to really make a difference. And there's nothing shameful about that. That's being intelligent, it's being considered, it's being careful, and you can document it appropriately, right? What you won't be benefiting by is stripping out all things, because then you're flying blind as far as performance. Okay, so here we have these first couple functions, and down here we have information that provides further details. So here we have, for example, information on update space. Update space here is called from run scenario. All 10,000 of its times it's being called from run scenario. Not surprising here. And it in turn is calling off to update cell here, and quite a, some of its time is being spent on several functions, but update cell, or several areas of code, but update cell is the biggest one. So of the 12 the 12 seconds associated with it. I think, to make sure that's a second, 10.87 of them are spent in update cell. Okay, so this is a little bit more specific. It's having to do with each function, what's costing it in terms of the things that it calls. So update cell in turn, here we have 10.87, so that same number. Seconds, I think, I'd have to go up there. And of that, 4.18 is being used in count surrounding live cells. Okay. In here we have more attention on count surrounding live cells, what it calls, what it's called by, etc. So more information, and as above, the information is documented, here down at the bottom. So these different columns here are described in terms of their meaning. And you can go into this, and I'm not going to do that in an exhaustive way. But this sort of information, ladies and gentlemen, is the sort of information that makes the real difference. This is the sort of information that allows you to be judicious in your decision making when it comes to performance, rather than to adhere to, certain simplistic rules of thumb, like always use C rather than a language like Java. This tells you where the costs are. This tells you what areas of your program you need to optimize, which areas of your program you might consider a different programming language, you might consider restructuring, etc. So let's use that information, shall we not? This profiling information is useful, and it's useful because we have functional abstractions. Let's use it. Count surrounding live cells. Let's go take a look at that code. So here we go. So we're going to go look at this one here, and hey, boom. Count surrounding live cells. That, just to remind you about why we're focusing on that based on what we just saw, I should have emphasized it, but if you look up at the top of this, count surrounding live cells is taking something like 50% of the time of the entire thing. So let's go figure out how to make that hurt less. Here's that code. Why is this hurting so much?
Double for loop.
Okay, double for loop. Let's step up one level. Why is something like 50% of the entire time being spent on this? Sorry? Gets called a lot. We talk about, and it's a very important concept, things being in the inner loop of a program. These are things that are called many, many times over the course of the program. So each particular invocation of this may be not too expensive, but it's being called many times. Now, as to why it is decently expensive, that's part of it, but part of it is where it's spending its time. And there's a double for loop here. What is it looping over here?
One to the left and one to the right. One
Yeah.
below and one above.
Yeah, so it's kind of looping over this. Okay, one to the up, one, easier drawn than said, right? Here we go. Okay. Okay, so here we're dealing with this cell. This is our row and call. And basically we're looping over this area here. Okay, we're taking a look at its surrounding eight cells, and we're counting the number of them that are live. And you'll notice that there's a special case here. Why is there this special case?
Don't count cell.
We don't count. In determining the count of the cells around us that are live, we only count ourselves. So this guy is excluded, right? This one's excluded, this gal. Okay. Okay, so what happens is we go through, and then what do we do for each of these cells in the surrounding area?
Check if it's legal.
We check if it's legal. And if it is legal, then we do what?
If it's occupied,
Sorry?
if the cell is occupied, so.
Yeah.
it's longer.
Yeah, it counts the number that are occupied, so if it's occupied, we bump up our count, right? Okay, now this code was written with generality in mind. I mean, you could very easily change it to have different coordinates. If we wanted a toroidal space, right? I pondered this. Maybe I should ask you to put in place a toroidal space, a space that wraps around. So if you go off the top, you come in the bottom. Go off the left, you come in the right. Vice versa, right? It's like a toroid. It's like a bagel or a donut, not a cruller. You know, like a donut with it's round, right? So you go around one way, so it wraps around. You can go around the other way, and we meet up, right? Okay. So if you wanted to do that, then is legal coordinate, could be changed, for example, in a quite simple way, and it could, an index for row call could then, great, index for row call could just immediately be updated to reflect the toroidal space, and you're off and running. And this code doesn't need to be modified at all. Great or not? Speak as in one voice.
Yes.
Yeah. Great, thank
Exactly
you.
as in one
I was
voice.
hoping you'd say great. Okay. Soon we may see that at press conferences in the States. Okay, so ladies and gentlemen, here we've written the code in a general way, but it's really pretty specialized, and actually, I mean, it's pretty it's pretty general, and maybe needlessly so for our needs. If we don't anticipate this evolving quickly, remember, so much of software engineering is designed to shield ourselves from changes, and if we don't anticipate likely changes along these lines, or even if we do, but we really have an even stronger need for performance, this is ripe for optimizing. What are some ways we might be able to optimize this? Okay, not ways the compiler optimizes it automatically, but that we might optimize this. Yeah.
You could unroll the loops.
Can unroll the loop. So rather than going through and creating these loops and sort of just go through three successive columns and three successive rows, we could unroll them. So I like that idea. How would that help? So by itself, I would argue, actually, it may be being done by the loop unrolling that takes place in the optimization anyway, by O3. So it may be that some of that is done, but it hides the fact that there's a hidden win there. Yes?
You don't have to call is legal coordinate.
Exactly. Ladies and gentlemen, there's a structure here that this is not capturing. This is legal coordinate is behaving in a very myopic sort of way. It's not taking advantage of the semantics of the situation. So it's asking each row and column, each of these, is it legal? Is it legal? Is it legal? Is this legal? Is that legal? Is that legal? Is that legal? And look, there's more structure to it than that. I mean, if we're on the top row, if this guy here, the one that's the center, is on the top row, then all of these are not legal. You don't have to check for each one. If we're on the left-hand side, each of the ones on the left is not legal. If we're on the right-hand side, each one's on the right. There's a structure to it, and we're kind of myopically checking, is this one legal, is this one legal? And it's unnecessary. We're doing a lot more work than we need to. And we're redoing that work each time. We're rechecking, am I on the last row for every single cell? We're redoing our work unnecessarily. But because that's hidden in another function here, it may not be obvious when it unrolls the loop. Unroll the loop, but each of those iterations that are unrolled. It'll reproduce this 9 times, but each of those iterations that are unrolled, it will call is legal coordinate, and recheck it in the part of that. Now, you could say, well, if it inlines is legal coordinate, it substitutes the body of is legal coordinate, which is conveniently, I didn't plan this, but it's down there at the bottom. It substitutes that in, that expression, right in there. You might say, well, unrolling the loop now will start to help it realize it doesn't have to recheck it if it's smart enough. But often when optimizations go on, one optimization takes place before the other. So maybe it does loop unrolling, and then it substitutes in, and by then it's not clever enough to go back and sort of realize, oh, I can remove this thing from the loop. So optimizations, like with -03, are not omnipotent. They have their limitations. The compiler is going to maybe only consider certain types of optimizations once, and if the opportunity arises later, it won't take advantage of it. But we can take advantage of it. We can be smarter than that. But there's another thing we can do here that reflects the semantics that's a very important general pattern that we can exploit. Does anyone see? I would argue that 99% of the time, 99 point, that's an under exaggeration, it's more like 99.99% of the time, the full generality of this is not needed. Why?
Because 99% of the time the sun won't be on the edge, right?
Sorry? It won't be on the edge. Yeah, it'll be on the interior. And then it is, as my Australian colleagues like to say, bog simple. I mean, if you're not on the edge, you're just dealing with a situation where you have 8 things to check and that's it. Boom. It's done. It's really these corner cases that are killing us, and yet we're checking them over and over and over. The legal coordinate, just, are we on the edge yet? Are we on the edge yet? Are we on the edge yet? We don't need to do that. We can basically check if we're on the edge up front, and if so, we can handle it in a straightforward way. Otherwise, we can go to the edge. So, ladies and gentlemen, I did that. We're not on the edge. Just add up the contents of those 8 neighbors. Either 1 or 0, add them up. Oh. The ones around it, right? If we are on the edge, okay, do your full work. Fine. I could have actually just put the original code in there. So if I run this, let's go see, to add a little bit of suspense. Okay, here we go. So ladies and gentlemen, so what I'm going to do is, here's Conway's Game of Life ugly on this computer. This is with, okay, I did it with O fast. I don't know if I want to do it with O fast. I'll do it with -03. I was fully ground last night. Okay. Notice I did it whole program. There's actually one that basically tells it, hey, this is the entire program. Why is that important?
It saves checking linkages between files.
Yeah, but it also means you don't have to preserve certain things that could be called by another module. Because if this isn't the whole program, maybe there's other modules that need to call into this one, and there's certain optimizations that aren't safe then. But if it knows it's the whole program, that gives it, extra. It knows it's the whole enchilada, so it lets it optimize it. Okay, here we go. Boom. This is the Conway's Game of Life ugly. Okay, and let's go run that. And let's go. Boom. Okay, this one here, ugly with 03 whole program. There we go. Boom. Okay, I'm redirecting into that just so we don't have to see the stuff. Okay, 3.9. Okay, 3.9 seconds. And you have to be a little bit careful with this. Make sure no other big programs are running. But we're going to be getting some pretty similar results, I think, run to run. Yeah, here we are. Okay, That's the ugly one. Now let's try this one, where we basically only optimized one method here. Okay? What do you think? One method. Have we sacrificed functional abstraction? Not in any significant way. We've just been intelligent about focusing our optimization efforts. Okay, so here we go. And we will go and compile that here. Okay. And we will go GCC it. Okay, that's the ugly one. Okay, here we go. There we are. And 03.
That's the file name.
Yeah, well, at least I don't have to worry about which is which. It's a little bit much. Okay, here we go. Boom. Okay, and now we will go and run that to our heart's delight. Here we go. And we'll run it. And what happens? Boom. Okay. .3. So up above, the ugly one was 3.9, 3.78. With just that one refactoring of that, even though the ugly code, even though the code of hideousness unwrapped, even though it optimized these things out, we were actually able to get our code perform at a level actually as good or better than the most optimized form of the ugly code.
You could optimize it more by putting in a no-checking version in there, but that'd be extremely difficult.
So we could optimize it more, but the big picture here is, ladies and gentlemen, I did not optimize it by saying, by going back to this and saying, to this and saying, oh, functional abstraction is for the birds. It hurts too much. Let's throw it out. We can't spare this performance cost. That's the lazy way out. That's the dangerous way out. That's the way that prevents you from knowing where it's spending its time. Prevents you from knowing where we need to optimize it. The way you get good performance is by structuring your code well, using the right tools like profilers, and using them with intelligence and judiciousness to restructure parts of the program. And if sometimes those involve deliberate, chosen, conscious sacrifices for small areas of the program, which sacrifice functional abstraction for the sake of performance for that small area, that's a very mature, sensible choice. But you don't do it by sacrificing it across all board in some benighted idea that somehow it's going to hurt us too much. No, functional abstraction lets you know where the performance bottlenecks are and lets you tune them and lets you replace. You'll notice what I did here. Rather than having to replace it in code which is ugly at two different places. These are both instances of that code conceptually. This is both count surrounding cells. But in my case, I only had to do it in a single place because of functional abstraction. So I was able to optimize it more easily. I was able to know where to optimize it. I was able to just plug in this new implementation because I was confident of what the other things depended on because of the specification. And I was able to do that because of good structuring of this program. So well-structured programs that use functional abstraction, ladies and gentlemen, actually give you performance benefits by letting you know where to optimize, letting you perform the optimization with least worry about how it's going to affect other areas of the code, and let you perform that optimization in an informed fashion that is modular. So functional abstraction here has given us actually the keys to improving the code quality. But that's not the only salient feature of this. Because, ladies and gentlemen, when we write code in a clean fashion, when we write code in a principled fashion that's well documented, it's divided up into pieces, that's well tested, we save ourselves time that otherwise is involved in debugging the code base, is otherwise involved in restructuring it, fighting against bugs. And the time we save, through that, we can invest in intelligent optimizations of that code. The observations that really matter, the high-level algorithms, the areas that are spotted as hot spots by profiling. And that allows us another level of performance advantage yet, because we've got more time to tune the code, because we've saved it from debugging and wading through confusing code, for code that's under-tested, etc. So don't get caught up in the siren song that, you know, the way to optimize performance is to sacrifice maintainability, to sacrifice understanding, to sacrifice well structure. That way, as Shakespeare said in King Lear, lies madness. Instead, it lies in a well-structured program that you can use a profiler on, that you can free up your time to really put in place the optimizations that matter. That's intelligent performance quest, rather than a kind of uninformed one that just assumes it's all too expensive. Performance. So, optimization, profiling as a tool, restructuring, and the cost of performance subtraction. It's not the simple trade-off that it's sometimes made off to be, and in many cases, it redounds to the benefit of functional abstraction. Okay? So let's put to bed those long myths that functional abstraction is too expensive. We can't afford functional abstraction. No, ladies and gentlemen, you can't afford not having functional abstraction for your performance. Okay? So, any questions related to this, or things you want me to discuss?
I have a confusion.
Yeah.
Gprof
Yeah.
text that you output.
Yeah.
I see that you have got the seconds rounded up. So when I ran the Gprof, I didn't get the seconds, but I did get the function calls. But I am not aware why I didn't get the seconds. I searched online, but I couldn't get any solution and stuff. Like I got this, I got the calls, the
Yeah.
number of calls, but I didn't get the seconds particularly.
You didn't
So
get these.
seconds, right?
Okay.
I got the function calls.
So was there simply a column that was empty there?
No,
Did
it's all zero. All
I have the same problem too.
okay. Did you run gprof? Okay, so that's interesting. Did you run it with the optimizations on?
no, without optimization, only the PG.
Only PG. Okay, here's a question. Was it in fact running with 50,000 steps?
Yeah. For the first code, I manually inserted it. For the second and third, I inserted the argument with
Yeah.
50,000 expressions. Yeah.
Okay, and it was taking a clear amount of time.
Yeah,
And-
I could see the steps. of
Yes,
1,000.
yeah, and it was taking
Yeah.
seconds to run. So I don't know. I've never seen that issue. The fact that two of you have experienced it suggests it's more than coincidence. I'd like to take a look at it, maybe after class, and see if I could reproduce it. I haven't heard on that about that before, but I'm intrigued. That's kind of a curious thing. Yeah. One thing I will say is that profiling itself has a cost associated with it. Right? Why does it have a cost?
You have to have monitors and tags in the code.
Yeah, and as we say, it instruments the code. It sort of inserts things into the code to keep track, among other things, of how many times something's called, or how much time is spent in each place. And that actually has a performance cost. So, you can't really observe the performance precisely without somewhat modifying the performance. And conversely, I should note that there are times where there's interactions between optimizations and that instrumentation, or there's, in other programming languages like Java, there may be times where that instrumentation can't be inserted for some reason or another. And there's limits to our ability to instrument code that we don't have access to. All we have access to is the binary library. So there's limits to that. As to why the seconds weren't shown there, even though it was running for a very material length of time, I'm puzzled. As I say, I'd have to look at it more. Yeah. Okay. Any other questions, comments? Okay. Great. So let's stop that and